In this video, I'm presenting kinetic and thermodynamic products and Hammett-Taft equation. Kinetic and thermodynamic products is not a past topic, so we are just going to see their basic in this video. Let's see. The basic difference between the kinetic and thermodynamic products is given here. You can see that the product, in case of kinetic product, the products are formed faster, and in thermodynamic products will be formed slower. So kinetic usually refers to something which something related to the formation of the product more faster, right? So that is why the kinetic products are formed faster. Now second point is kinetic products have low activation energy. Their activation energy is low, that is the reason the products are formed faster and usually form at low temperatures. Since the activation energy is less, so energy required will be less, and so the activation energy is low and usually form at low temperatures, that means 0 degree or even less. But thermodynamic products are those products which have high activation energy, and that is why the products are formed slower and usually form at high temperatures. The thermodynamic products will be formed at the higher temperatures. Why? Because the activation energy is high for the thermodynamic product. Now for the kinetic product, we will see that the product is unstable. If the product is unstable, then obviously what the energy of the product is high. So kinetic products have higher energy while the product of thermodynamic is stable. That means the product is having less energy, because if the energy of the product is less, then only the product is stable. The fourth point in the kinetic product is that it proceeds by 1-2 addition. We are just going to explain it through one example later on. And in case of thermodynamic, it proceeds to 1-4 addition. So we need to remember this, that kinetic are 1-2 addition and thermodynamic follow 1-4 addition. Now the fifth point for kinetic product is that the product consists of terminal double bond. They will consist of terminal double bond, but the thermodynamic products consist of internal double bonds. So this is the main differences between the kinetic product and the thermodynamic product. So come, let us see how this all the point of differences can be justified. So let us take one example for this. So the best simple example is that the reaction of 1,3-butadiene. So 1,3-butadiene, when it is reacted with HBr, then there is the probability of forming two products, so at two different conditions. So suppose the reaction is carried out at 0 degrees Celsius, then we are going to get a kinetic product as the major product, which is shown above. So secondly, if the reaction is carried out at quite high temperature, then that is 40 degrees Celsius, then we are going to get the major product, which is a thermodynamic product as shown below. So let us check their mechanism, how this product formation is carried out, is done. So the 1,3-butadiene, its resonance can be drawn in this way. Suppose a double bond has shifted to the first carbon atom. Let us number it 1, this is 2, this is 3, and this is 4. So it becomes here negative and this is here positive. The double bond will be, this double bond particularly will be unaffected. So you can see that this is a secondary carbocation, and another resonance that is possible is, suppose this double bond shifts to the second carbon, then you will find that this becomes here positive will be there in this carbon atom. So we have numbered it 1 for this, 2, 3 and 4. Similarly, this is 1, this is 2, this is 3, and this is 4. So you can see here that this carbocation is a primary carbocation, and we know that tertiary carbocation are more stable compared to secondary, and secondary carbocation are more stable to primary carbocation. So this is one reason why the kinetic product is formed faster, because the bromine will attack at the secondary, I mean the secondary carbocations faster, because the secondary carbocation is more stable. So if it is more stable, less energy is required, so here the kinetic product is formed faster. But the primary carbocation that is less stable than the secondary carbocation, it will be formed slower. Now here one thing we have to remember is that still the primary carbocation, which gives a thermodynamic product, is more stable than the kinetic product. But if we see that the kinetic product has transition state of the secondary carbocation, which is more stable than the transition state of the primary carbocation, primary carbocation of the thermodynamic product. So still the thermodynamic product, which has the higher transition state due to its less stability of carbocation, that is primary carbocation, still this is the major product. Why it is still the major product? We have to know this one, that there is one rule that is known as Set-Zep rule, which we basically find in most of the organic reactions. So according to Set-Zep rule, the more substituted alkene are major product. Okay, more substituted alkene are major product. If you see this thermodynamic product, then you will find that in simple sense what we can say, that the carbon atom present attached to the double bond, if the number of carbon atom increases in between the double bond, that product will be major. So here in this case we have this is a carbon double bond. Here we have one carbon and here we have another carbon, so there are two carbon atom. Okay, but if we see our next product, that is the kinetic product, then we will find that in kinetic product, which was this one, this is our kinetic product. You can see that this double bond is surrounded by only a single carbon atom. This double bond is surrounded only by a single carbon atom, so it has only one carbon atom, so it is less substituted. But according to Set-Zep's rule, the more substituted carbon atom are the most favored product, that means they will form as the major product. Okay, which in case of thermodynamic product, we can see that there are two carbon atoms surrounding to this alkene group. Okay, so that is why here the Set-Zep rule will govern in determining the major product. Okay, so we have also seen that this is our kinetic product and this is our thermodynamic product. We said in the point, we have said that the kinetic product, they will consist of terminal double bond. So you can see here that there is a double bond in the terminal position, and the thermodynamic products, they consist of internal double bonds. So we can see here that there is a internal double bond in the thermodynamic product. Okay, so this is a thermodynamic product and this is a kinetic product. So let us see their energy profile diagram. This is the energy profile diagram. You can see that at low temperatures the product distribution will be related to the relative energies of 1, 2 and 1, 4 transition state. EA is the activation energy given here. At low temperatures, the product distribution will be related to the relative energies of the 1, 2 and 1, 4 transition states. EA is the activation energy. So you can see this is a transition state, 1, 2 transition state and 1, 4 transition state, right? This is a 1, 4 transition state and 1, 2 transition state. So you can see that this particular thing is the transition state for 1, 4 transition state. It means a thermodynamic transition state. And I said, I have told that the the thermodynamic product, they will have higher transition state due to higher transition state means higher energy due to higher energy base primary carbocation. Due to the primary carbocation, they are having higher transition state. But kinetic product, they are followed by the secondary transition state, secondary carbocation. So they are more stable, so they will have lesser energy. Okay, so this is what is shown here, the transition states of the two products. So this is all about the kinetic and thermodynamic products, and this is a very simple, not a vast topic. This much knowledge is enough to understand the kinetic and thermodynamic products. So now let us move on to the next topic, that is the Hammett equation. What is Hammett equation? So this equation describes the linear free energy relationships, that means LFER, between the reaction rates and the equilibrium constants in organic reactions involving meta and para substituted benzoic acid derivatives. So Hammett equation is given as log kx by log naught, log kx by k naught is equal to sigma rho, or more precisely we can write rho's summation of sigma, where k is the equilibrium constant for a para or meta substituted benzoic acid. Actually it should be kx. Okay, kx is the equilibrium constant for the meta and para and meta substituted benzoic acids. You can also see here that k naught is the equilibrium constant for unsubstituted benzoic acid. The rho is here called the reaction constant. The rho is called the reaction constant that only depends on the nature of reaction and not the substituent. And sigma is called the substituent constant. Its value depends on substituent used and gives the measure of substituent's ability. What it gives? It gives the measure of substituent's ability to dissociate the parent benzoic acid. Both terms on the right hand side, that means sigma and rho of Hammett equation, gives the electronic effects. So sigma and rho, they are nothing but they are electronic effects such as polar effect, resonance effect, field effect, etc. of the substituents on the reaction rate and structure of the parent compound, that is the substituted benzoic acid. So what is said here, let us understand it. So Hammett equation is given by log kx by k naught, which is equal to sigma rho. Okay, so here kx is the equilibrium constant for substituted benzoic acid. Okay, here benzoic acid is the parent compound. That means we are taking it as a reference compound. Okay, and k naught is unsubstituted benzoic acid. The equilibrium constant k naught is the equilibrium constant for unsubstituted benzoic acid. So kx is the kx is the equilibrium constant for substituted benzoic acid, whereas K naught is the equilibrium constant for unsubstituted benzoic acid. So here again we will try to know some important things. So this thing which we have written, that log of Kx by K naught is equal to sigma rho. This can be split up log Kx minus log K naught is equal sigma rho. Sigma is the substituent constant, okay, substituent constant, and this rho is the reaction constant, okay. So sigma means it will depend on the substituent that is used, but rho will not depend on the substituent used. It will simply depend on the type of the reaction that is carried out. So from this we also know one thing, that pKa, acidity, the value for acidity of a compound is written as minus log of Ka. This relation is known to us. So if this relationship is known to us, then this can be written as minus pKx and this can be written as minus. So since here already we have minus, so we can write simply pk naught. So overall what we can write is pkx minus pkx plus pk naught is equal to sigma rho. So this can be written as rearranged as pkx is equal to pk naught minus sigma rho. So from Hammett-Taft equation we can get this relationship. So we can find the acidic value for the given compound using this equation, which is derived from Hammett-Taft equation, because this term is still remaining, okay. This is the values of the benzoic acids, substituted and unsubstituted benzoic acids, and it is also said that this complete term is nothing but electronic factor, okay, electronic effect. There are two effects, that means electronic effect and the static effect. So this is a electronic effect, okay. So let us solve some questions related to the Hammett equation. So the question is this one. The question is like the pKas, that means pKa of a benzoic acid and para-hydroxybenzoic acid are given 4.20 and 4.57. The value of sigma for OH is, so what is the value of sigma for OH? Let us see how we solve this one using that very concept that we have discussed. So we know that pKx is equal to pk naught minus sigma rho, that is from Hammett equation. So it is for the benzoic acid we have 4.2, that means benzoic acid means it is a pure benzoic acid, not substituted, okay. It is an unsubstituted benzoic acid, and this value is for unsubstituted benzoic acid, that means 4.20, okay. And para-hydroxybenzoic acid, that means substituted benzoic acid, the value for rho, I mean the value for pK is given 4.57. So this is the substituted benzoic acid, that means it may be para or it may be meta benzoic acid. Okay, this is a substituted benzoic acid. So for this pK value is given 4.57, so it is 4.57. And always remember one thing, that the raw value for benzoic acid is taken as 1, and for phenol the raw value is equal to 2.25. This is a fixed. Okay, you have to remember that. So here what we are going to see, let's solve it. It is a very simple question. Ultimately pkx minus equal to pk naught minus sigma rho. This means that pkx, which is for a substituted benzoic acid, we have 4.57. so 4.57 is equal to, for unsubstituted we have 4.20 minus sigma, and I have said for benzoic acid rho is equal to 1, that means into 1. So we have to find sigma value for OH. So this will be the sigma value for OH, it will give. Okay, so this means sigma is equal to 4.20 minus 4.57. okay, this will give us 0 minus 0.37, right? So 0.37. so here the option B will be correct. Let's move on to the next question, that is this one. pKa values for 3 and 4 methoxybenzoic acids are given as pKa for 3 methoxybenzoic acid is 4.07, and pKa for 4 methoxybenzoic acid is 4.46, and for pure benzoic acid, it means unsubstituted benzoic acid, is 4.13. Then you calculate sigma m, sigma p. M means meta and p means para substituted for OMe. Okay, that means the compound is 3,4 methoxybenzoic acid. That is benzoic acid. Okay, 1 2 3, that means here OMe. This means this is the 3 methoxybenzoic acid, and when it is, so this is a 4, if it is here OMe, that means it is a 4 methoxybenzoic acid, this one, right? So their pK values is given, so we have to calculate sigma m and sigma p, para substituted and meta substituted sigma values. And for normal benzoic acid, unsubstituted benzoic acid, is given 4.19. The value for pK is 4.19. so let us do it. Similarly we can get pK, suppose this is pkx is equal to pk naught, that is equal to sigma rho. Sigma, first of all let us find for meta rho. So this means the pkx, it is said the value for, if it is meta then it is m here. So for meta position, that means 3 methoxybenzoic acid, we have pK value is 4.07. okay, so 4.07, that is equal to pK naught, that means for unsubstituted benzoic acid 4.19. okay, minus sigma m into, I have told for benzoic acid is always 1, rho is taken as always 1, so it will be 1. Sigma is equal to, then we are getting 4.19 minus 4.07, so whose value is equal to 0.12. so for sigma m we get 0.12. okay, similarly for sigma P, we can do the same procedure. pkx para is equal to pk naught minus sigma rho. Rho is always 1. pk for substituted methoxy benzoic acid. P means para, so this one 4.46, that is equal to, it is given 4.19 minus sigma p, this is into 1, so sigma is equal to 4.19 minus 4.46, so we are getting its value minus 0.25, so this is the value for sigma p, which is equal to minus 0.25. so this is a very simple question. Okay, let's move on to the next is the Taft equation. So this is something which I have written for the Taft equation. If you can see here, the equation accounts for field, inductive and resonance effect, which are electronic effects, while the Taft equation describes the steric effects of the substituents. Okay, so this thing is what basically you can see it later on. This thing is what I'm going to explain it. Okay, you see what is Taft equation. Taft equation is nothing but is just the modified version of the Hammett equation, because Hammett equation we know that it is given as log kx by k naught is equal to sigma rho. Am I right? Now what is Taft equation? Taft equation is very much similar to Hammett equation, but just a bit modified version. On what basis it is modified version? Here it becomes sigma star plus del es. Okay, so what are these terms actually? As I have already told that this is a Hammett equation. In the Hammett equation, this right hand term is completely electronic term. Okay, electronic effect, it is signifying as electronic effects. But what if the substituent also has some steric effect? Okay, so in most of the compound we will find that the bulky nature, in most of the bulky complexes we will find that there is a influence of steric effect on the reaction. So obviously that Hammett equation has some drawback. So in order to meet the correction to the Hammett equation, the new equation was introduced by, so new and modified equation was introduced by the Taft, and this is known as Taft equation. So he have introduced this term delta es. Okay, delta es is the steric factor. That means we can say it's steric effect. This has arisen due to the steric effect. Okay, completely steric effect. The first part is electronic effect, and the second part that the delta is called a reaction constant that describes susceptibility of reaction by steric effect. Okay, and these are the values how we can describe it. So the Taft equation which we have got as kx by k naught is equal to sigma star rho star plus del es. Okay, del es is here substituent constant. Okay, substituent constant, sorry, es is a substituent constant, and del is known as a reaction constant. Now this reaction constant is what, and sigma is known as the polar substituent constant. Okay, and this is a sensitivity factor here. Both these terms signifies the electronic factor. Okay, and this term signifies the steric factor. Now this delta, I have said it is a reaction constant. Now it gives the measure of the susceptibility of the reaction to the steric effects. That means the chemical reaction, the steric, how the steric effect can influence the chemical reaction, its measure is given by the delta. Okay, and Es is nothing but the steric effect of the substituent. Substituent is suppose bulky one, then that bulky substituent uh, will have different value for Es. Okay, these are the basic things of Hammett-Taft equation. Hope you guys like this video, and if you like this video then please subscribe my channel. Thank you.